But these are very low modulus mesh-like particles that are very deformable. They're never going to hold a drug just through sequestration because there's too much mesh size there and they could leak out. So what we're beginning to do is thinking about ways of conjugating drugs. We're also interested in now moving these particles down to smaller sizes. And so here's now, out of the same degree of softness, these types of particles at 200 nanometers, 80 by 190 nanometers, these filamentous particles, and we're now systematically going through and trying to develop a biodistribution map as a function of size, shape, and modulus in these systems. Well, obviously, there's a lot of interest in being able to conjugate drugs and bringing drugs into these types of systems, whether they're biological or small molecule toxins. Obviously, I've shown you we've been using different types of imaging beacons for some time. And so we're interested in, with these very soft particles, that we're going to have to covalently attach the drug because the mesh size is too high. There's obviously a lot of different pro-drug strategies that people have used in the literature for linking a drug to some drug delivery vehicle, whatever it might be. These all have some challenging issues. We, on the other hand, have developed a novel linking chemistry that is based on simply silyl ethers. Organic chemists have been using silyl ethers for many, many years as a protecting group. We like to use it as a pro-drug linking strategy. And as one varies the substituents on the silicon atom, you can change the rates of hydrolysis over 7 orders of magnitude, from dimethyl to T-butyl, and use that way to control the release of the drug separate from the biodistribution of where the particle's going, and try to combine all these into a common strategy. And I'll just show you one example of a drug that we're doing this approach with, a Camptothecin type drug with a silyl ether linker group, and we covalently attach this into these soft deformable particles. So this is the kinds of experiments that are ongoing now. When you can start linking drugs or trapping drugs into these particles, it can be like a Trojan horse if you're looking at an intracellular uptake mechanism. This is particles loaded up with drug, and we can design the chemistry such that the drug only comes off in the lower pH inside a cell versus the higher pH outside the cell. We start using stimuli of internalization for deleting drugs. And this is a YouTube quality video here that we love to stare at. And there's a lot of detail here I'd love to walk you through at some point, but let me move on. When we think translationally, a lot of people for the FDA are going to want matrices that they're used to dealing with. And PLGA, Bob has been using PLGA for a long time. It's the same material as our bioabsorbable stent, same material as bioabsorbable sutures. Typically, to trap drugs in PLGA, there's the classic sort of coacervation or emulsification or micellization approaches for using these types of systems. What we typically do is we draw films of these types of polymers with different types of drugs if we want to use PLGA as a matrix. We have to work under conditions where this film is homogeneous, because if we have phase separation where we're making very small particles, we'll have a heterogeneous population of particles. But when we do this right, we can now make particles of extraordinary control. This is simply PLGA and docetaxel, and we have encapsulation efficiencies that are derived from the simple molding process that are very high relative to kinetically trapping the drug. These are all the same size, all the same shape, but they vary dramatically in drug content, from 40% drug to no drug. We keep the size constant, we keep the zeta potential constant. And it has dramatic effects on the ability for dosing. This is empty particles, and then as we increase the amount of drug, these particles get more and more potent, and we can increase the potency versus Taxotere by several orders of magnitude by getting the drug content up, and this is plotted against drug concentration. So we're getting to the point of single particle cell deletion using these types of approaches. We're beginning to now look at the biodistribution of what I would call as a hard particle, PLGA, versus the soft ones I just showed you. These are different size particles. We're looking at biodistribution. This is percent recovered dose. This is a little hard to read. This is tumor. So we're in the order of 10 to 15% of these particles at 24 hours accumulating in tumor. We still have 30 to 35% of the particles in circulation at 24 hours. This is an SKOV3 xenograft system. So we're trying to combine all these systems and begin looking at different type of efficacy. We're looking at different types of tumors. Each of these tumors have different fenestration characteristics, sort of in a Rakesh-Jain-like approach, looking at, with precision tools, trying to classify tumors, different sizes, different shapes, different deformability, how we can penetrate these different types of systems. And now begin going, even with PLGA, to these different sizes and a whole host of different sizes with simply PLGA particles loaded up with these drugs, and this is the direction that this is all going. We're starting to do some of our very first treatment. This is an intratumoral injection model. These are some mice. This is controls. This is Taxotere, and this is one of our very first systems. And we're getting some performance. We've got a long way to go yet, but it's early days in this strategy. One of the drugs that obviously people are very interested in are nucleic acid systems. These are siRNA. We cast films of siRNA and PLGA, making these simple systems. We don't pre-complex or make polyplexes. We make these films of PLGA and siRNA. We then harvest those with different types of lipids, and I'm showing you some commercial lipids of DOTAP and DOPE. We can add excess of these, and then we basically wash off all the excess. So we're close to sort of a monolayer of lipid on these particles, and these become very effective transfection agents. These are luciferase-expressing HeLa cell lines. We're getting into sort of single-digit nanomolar EC50 values, delivering siRNA relative to our controls. And we think we can do this with a wide variety of systems. We think we can do this with a wide range of different types of particles, and we're beginning a range of in vivo experiments, taking a page out of Bob Langer's approach. This was an intratumoral injection model, a luciferase-expressing tumor line. This is a control panel here on the left that's a naked siRNA. This is an irrelevant sequence, and then this is the experimental arm showing a protected luciferase system, and we see a 50% diminution in the bioluminescence. And so we're beginning to work through these systems in a variety of different approaches. So that's all systemic delivery. Let me end on one last topic. As somebody is trying to get drugs into solid tumors, this is a real challenge. This is a real challenge whether it's a particle or a small molecule. And as I told you, Bob and I were doing some interventional cardiology with the stent work. And so we have launched a program to start taking the tools of interventional cardiology, minimally invasive tools, as a way of delivering locally or focal delivery of drugs using an electric field. So this is ionophoretic delivery, mild electric current to assist the local delivery of different types of drugs. Tuvesin's laboratory is going to speak later this afternoon. He had this seminal paper in Science this past summer showing that, in fact, pancreatic cancer is one of the most challenging. This is a poorly vascularized tumor. It's shrouded in what he referred to as a fortress. But through hedgehog signaling pathways, if you could eliminate that fortress, you find that these pancreatic cancer cells are very susceptible to gemcitabine. But it's a delivery issue of getting that drug to these systems. So we've embarked upon a multi-faceted approach to design minimally invasive devices using a variety of different approaches, intravascular, endoscopic, and laparoscopic approaches, designing new types of devices, working with large animals. Like for stents, you have to work in a porcine model for device safety, but obviously there are no cancer models in large animals, so we have to do combinations of small animal studies with large animal studies. And I just want to show you a quick glimpse of some new work. This is a surgically implanted device. This is a semi-permeable membrane that's ionic. We call this an originating electrode. This is a counter electrode. Drug flows in through a 4-lumen tube here. We circulate the drug out, we apply a current, and we basically use electric field to drive drugs into these poorly vascularized tumors. This is a canine model, and we apply current for 60 minutes, and we compare IV infusion. And we can have tremendous increases in the amount of drug that we load up into these different types of organs. A 12-fold increase in the amount of drug, gemcitabine, into the pancreas with current than without current. And this is how much gemcitabine gets into the pancreas when delivered by IV. And so we have tremendous increases in the amount of drug that we deliver. And the key is, when we deliver drug locally, we find no drug systemically. We're below limits of detection. So it's a focal delivery of the drug and gives us huge opportunities with doing that. We've now extended this to xenograft tumor models. We've miniaturized our device. This is a 3-millimeter device. This is on a patient-derived xenograft tumor in a mouse, and we're getting the same sort of results. We have tremendous increase of, this is actually now in the tumor, of gemcitabine in the tumor. And then when we do the IP approach that the Tuvison laboratory demonstrated, we get no drug in the tumor. And so we're beginning to use these tools for delivery. And we think beyond pancreatic cancer, there's a whole bunch of different cancers that we begin exploring and delivering drugs, antibodies, and particles. So with that, let me end. I think the key is there's great opportunities for engineering and applied chemistry for delivering a lot of different types of approaches, whether it's small molecules to biologics. We think the tools from the microelectronic industry gives us the precision and uniformity that heretofore has not been available in the particle world, and we think that size, shape, and modules can bring new insights in different types of treatments. I'm fortunate to have a terrific group. This is a partner in crime, Mary Napier, who runs our laboratory, a lot of different collaborators, and a great group of students, and a postdoc here with me, Wefta Hassan is with me, and she's done a lot of this work. Vision without resources is just a hallucination, and fortunate to have great support from NIH, our CCNE, and financial support from Liquidity and NSF. And with that, I thank you, and thank you for letting me participate in your program.